Let me show you something. I take this top, I set it on the table, I don't spin it, and I let go. What happens? It falls over. Immediately. Like a drunk at closing time. There is nothing surprising about that. Gravity pulls it, it tips, it clatters. It's done. Now I do the same thing, except this time I give it a spin first. A good hard spin. I set it down on its point, I let go, and it stays up. Not for a flicker. It stays up for 10, 20, 30 seconds. Maybe a minute if it's a well-made top. Standing there on its little point, balanced, proud, serene, defying everything your gut tells you should happen. Why? Think carefully before you answer, because I promise you, the first thing that comes into your head is wrong. Most people say something like, well, the spinning creates a force that holds it up. Okay, what force? Point to it. Tell me which direction it acts. Tell me which molecules of air or which particles of table are exerting this mysterious extra force. You can't, because that's not what's happening. There is no upward force created by spinning. None. Zero. The weight of that top is exactly the same whether it's spinning or not. Put it on a kitchen scale, spin it as hard as you can, and the number doesn't budge. Not by a fraction. Gravity hasn't changed its mind. The table pushes up with the same normal force it always did. Nothing new has entered the picture in terms of forces. Some people try a different explanation. The centrifugal force pushes the mass outward, and that somehow stabilizes it. This is also wrong, and I want to explain why in some detail, because it's a seductive mistake. Centrifugal effects do push mass outward from the spin axis, that's real. But outward from a vertical spin axis means sideways, horizontal. That doesn't help you fight gravity, which pulls vertically. Pushing mass sideways doesn't prevent tipping. It's like trying to stop a tree from falling by tying a rope around it and pulling the rope along the ground. You just drag the tree sideways. You need to pull up, and spinning doesn't pull up. So something genuinely strange is going on. Something subtle, something beautiful, something that I think is one of the most underappreciated results in all of classical mechanics. And here's the good news, you can understand it completely. Every piece of it. But you have to be willing to let go of your first instinct, because your first instinct is pointing you in entirely the wrong direction. Let's start over. Forget the top for a moment. I want to ask you something so simple it sounds silly. What does it mean for something to fall over? I take a pencil, I stand it on its point on a table, and I let go. It falls, obviously. But I want you to describe to me very precisely what happened. Not vaguely, precisely. Here's what happened. The bottom of the pencil stayed roughly where it was, on the table. The top of the pencil swung outward and downward. The pencil didn't slide across the table, it didn't translate, it pivoted. It rotated around its base. That's what falling over means. Falling over is not a thing moving downward. Falling over is a thing rotating around a pivot point. Now what caused that rotation? Gravity did. But not just gravity as a downward force. Think about it this way. Gravity pulls on the center of mass of the pencil, which is halfway up. The base of the pencil is stuck on the table by friction. So you've got a force pulling on a point that's some distance from the pivot, a force applied at a distance from a pivot. In physics, that combination produces something called torque, a twisting influence, a rotational push. Torque is the rotational version of force. Force makes things accelerate in a straight line. Torque makes things accelerate rotationally. They're related, they're cousins, but they are different animals, and confusing the two will get you into trouble. Here's a way to feel the difference. When you open a heavy door, where do you push? At the handle, far from the hinges. If you push right next to the hinges, you'll struggle, even though you're applying the same force. Why? Because torque depends on distance. Torque equals force times the distance from the pivot, times the sine of the angle between them. Push far from the hinge, big torque, easy rotation. Push near the hinge, small torque, hard rotation. Same force, different result. That's the power of torque. So the pencil falls because gravity, acting at a distance from the base, produces a torque. That torque causes rotational acceleration. The pencil starts to rotate faster and faster, swinging around the base, until it smacks the table. Done. Over. No mystery. Good. So falling over equals rotation caused by gravitational torque. Tape that to the inside of your forehead. Now let's go back to the top. The top is sitting on its point, tilted slightly. All real tops are tilted at least a little. Gravity is pulling the center of mass, which is above and to one side of the contact point. That produces a torque around the contact point. The torque is trying to rotate the top to tip it over to make it do the same thing the pencil did. When the top isn't spinning, the pencil thing is exactly what happens. Torque causes rotation. The top rotates. It falls. Over. Done. But when the top is spinning, the same torque is still there. I want to emphasize this. Gravity hasn't gotten weaker. The distance from the pivot to the center of mass hasn't changed. The torque is exactly the same. It's still trying to rotate the top. So the question isn't what holds the top up. That's the wrong question because it assumes something is fighting gravity. Nothing is fighting gravity. The right question is, what happens when you apply a torque to something that is already spinning? And the answer to that question is one of the strangest, most counterintuitive, and most beautiful things in all of mechanics. Let me build up to it. Forget tops and gravity. I want you to imagine a bicycle wheel. You've got a bicycle wheel removed from the bike, and you're holding it by the axle, one hand on each side. Somebody has given it a good hard spin. The wheel is spinning fast. Now try to tilt the axle. Try to pitch the wheel to the left. Push your right hand forward and your left hand back like you're turning a steering wheel. If the wheel were not spinning, this would be trivial. The wheel would tilt left, obediently, boringly, predictably. It would just go where you push it. But the wheel is spinning, and when you try to tilt it, something deeply, viscerally strange happens. The wheel doesn't tilt left. It doesn't resist going left by pushing back to the right, which is what you might expect from stiffness or inertia. Instead, it tries to twist in a completely different direction. It tries to yaw, to turn on a different axis entirely. You push left and the thing goes up or down. You push forward and it goes sideways. Every direction you push, the response is 90 degrees off from where you intended. You feel this in your wrists and forearms, and it is deeply unsettling the first time you experience it. The wheel feels like it has intentions of its own, like an invisible hand inside the hub is redirecting every input you give. I've watched students pick up a spinning bicycle wheel for the first time, and the expression on their faces is always the same, bewildered amusement, because their muscles expected one thing and the world delivered something completely different. So why? Why does a spinning object respond perpendicular to where you push it? To answer this, I need to talk about angular momentum. Not as a formula, not as an abstraction, but as a physical, pointable, visualizable thing. When the bicycle wheel is spinning, every tiny piece of the rim is moving. Let me place a clock face on the wheel. The piece at 12 o'clock is moving, let's say to the right. The piece at 6 o'clock is moving to the left. The piece at 3 o'clock is moving downward. The piece at 9 o'clock is moving upward. Every piece of the rim is in motion, and they're all coordinated, all orbiting in the same direction. This collective rotational motion has a total amount and a direction. We represent it with a single arrow, a vector, called angular momentum. The arrow points along the axis of rotation. Which direction along the axis? We use the right-hand rule. Curl the fingers of your right hand in the direction the wheel spins, and your thumb points along the angular momentum vector. For our wheel, let's say the angular momentum points to the right, along the axle. The magnitude of the angular momentum depends on how much mass the wheel has, how far that mass is from the axis, and how fast it's spinning. More mass, wider radius, faster spin, all mean more angular momentum. A big heavy wheel spinning fast has a huge angular momentum. A tiny light wheel spinning slowly has a small one. Why do we represent rotation as a vector at all? Rotation happens in a circle, in a plane. Why point an arrow perpendicular to that plane? The reason is both practical and deep. Any rotation in 3 dimensions has a natural axis. The axis tells you the direction of the vector, and the spin rate tells you the magnitude. This representation is powerful because it lets you add rotations by adding vectors, and it lets you apply Newton's laws to rotation in the same mathematical form as straight-line motion. It also reveals something invisible. If you think of rotation as just going in circles, 2 rotations around different axes don't combine the way you'd expect. If you spin a wheel around one axis and then try to add spin around a different axis, the result is spin around a third axis different from both originals. Vector addition handles this automatically. You add the 2 angular momentum arrows, and the resultant arrow tells you the new axis and speed. This is critical for gyroscopic behavior because precession is precisely the continuous addition of small angular momentum changes to a large existing vector, and the way vectors add is what makes the axis sweep in a circle instead of tipping over. Now, here comes the crucial principle. The one thing that explains everything. Newton's second law tells us that force equals the rate of change of momentum. Push on something, and its momentum changes in the direction of the push. There's a rotational version of this law. Torque equals the rate of change of angular momentum. Apply a torque to something, and its angular momentum changes in the direction of the torque. I need you to hear that very carefully. The change in angular momentum happens in the direction the torque points, not the total angular momentum. The change, the little nudge, the delta. This distinction between the total and the change is everything. It is the entire explanation for why spinning things don't fall over. So let me drill into it with an analogy from ordinary straight-line motion. Imagine a bowling ball rolling across a gym floor heading north. It's got momentum pointing north. Now somebody comes along and gives it a kick to the east. Not a huge kick, just a tap. What happens? Does the ball suddenly go east? No, it was going north with a lot of momentum. The kick adds a little bit of eastward momentum, so now the ball's total momentum is mostly north plus a little bit east. The ball curves slightly to the northeast. It doesn't abandon its northward motion. The change in momentum is to the east, but the total momentum is mostly still what it was before, just slightly redirected. Now make the ball heavier. Give it more northward momentum. Same eastward kick. What happens? Even less deflection. The ball barely changes course, because the change in momentum, which is the same kick, is now a tiny fraction of the total. The heavier, faster ball is more resistant to having its direction change. Not because any force is fighting the kick, but because the same kick represents a smaller relative change. This is exactly what happens with a spinning top. The top has a big angular momentum vector pointing up along its spin axis. Gravity applies a torque. And here's the crucial geometry. That torque points sideways, horizontally, perpendicular to the way the top is leaning. I'll explain why in detail shortly, but take it on faith for a moment. So the change in angular momentum is sideways. A little bit of horizontal angular momentum gets added to the big upward vector. What happens to the total angular momentum? It was pointing straight up. Now it's pointing very, very slightly to the side. The tip of the vector has moved sideways by a tiny amount. Physically, this means the spin axis of the top has shifted slightly sideways. Not downward, sideways. The top hasn't tipped. It has rotated its axis horizontally by a tiny angle. And now what? Gravity is still pulling. The top is now leaning in a slightly different direction. So the torque, which always points perpendicular to the lean direction, has also rotated. It's now pointing in a new sideways direction. So the next little nudge to the angular momentum is in this new sideways direction. And the next one is perpendicular to that, and the next one perpendicular to that. Each nudge is perpendicular to the current direction of the angular momentum vector. Each one pushes the tip of the vector sideways relative to where it currently points. What path does the tip trace out? A circle. The angular momentum vector sweeps around and around, horizontally, maintaining its upward tilt going in a steady circle. That slow, stately circling of the spin axis is called precession. And precession is the reason the top stays up. The top doesn't fight gravity, it doesn't resist the torque. The torque is fully active, fully effective, doing exactly what torques do, changing angular momentum. But because the angular momentum is large and the torque is perpendicular to it, the change is a slow sideways drift of the spin axis, not a downward collapse. The top is falling. Let me say that plainly. The top is falling. Gravity is pulling, torque is acting, and the top is responding. But it's falling sideways, and falling sideways in a continuous circle is the same as staying up and going around. That's the trick, that's the whole secret. Precession is falling sideways forever. Let me now explain the geometry that I asked you to take on faith. Why does the torque from gravity point sideways? Picture the top leaning to the right. The center of mass is up and to the right of the contact point. Gravity pulls the center of mass straight down. The contact point is fixed on the table. What rotation would gravity cause if it could? It would swing the center of mass downward, rotating the top around a horizontal axis that passes through the contact point and runs perpendicular to the lean direction. If the top leans to the right, the axis of the rotation that gravity would cause runs from front to back through the base. The torque vector by the right-hand rule points along this axis. So the torque vector is horizontal, pointing either toward you or away from you. Not downward, not to the right, perpendicular to both the direction of gravity and the direction of the lean. This is the geometric fact that makes precession possible. The torque is perpendicular to the angular momentum. A perpendicular nudge to a vector doesn't make it longer or shorter. It only changes its direction. The angular momentum vector rotates without changing magnitude. It sweeps around and around, maintaining its length, like the hand of a compass. If the torque pointed in the same direction as the angular momentum, it would speed up the spin or slow it down. If it pointed opposite, it would decelerate the spin. But perpendicular torque does neither. It only redirects. and continuous perpendicular redirection traces a circle. That's precession. How fast does the precession go? Let me give you the rough argument, because it's simple and it reveals something elegant. The torque from gravity is approximately the weight times the distance from the pivot to the center of mass. Call it tau. The angular momentum of the spinning top is L. The precession rate, how fast the axis sweeps around the circle, is approximately tau divided by L. That's omega precession equals tau over L. Look at what that tells you. The faster the top spins, the bigger L is, and the smaller the precession rate. A rapidly spinning top precesses very slowly. It looks rock solid, as if it's nailed in place. A slowly spinning top precesses fast, and you can see the axis sweeping around visibly. This also tells you something satisfying about the limiting cases. When the spin is very fast, L is enormous, the precession rate goes to zero, and the top essentially holds still. That matches intuition. A fantastically fast spin should stabilize the top completely. When the spin is very slow, L is small, the precession rate is very large, and the top whips around its precession circle rapidly, the axis is swinging wildly, and the top is about to fall. That also matches what you see when a top is winding down. The wobble gets worse and worse until the top gives up and drops. There's a beautiful intermediate regime where the precession is clearly visible but the top is still stable. That's the regime where spinning tops are most fun to watch. The axis traces a slow, graceful cone while the body spins underneath it. Two rotations superimposed, the fast spin around the top's own axis, and the slow precession of that axis around the vertical. Now let me tell you about a subtlety that shows up in real tops. If you watch carefully, especially right at the moment you release the top, you'll see a little bobbing motion layered on top of the precession. The axis dips down slightly, then bobs back up, dips, bobs over and over while it precesses. This bobbing is called nutation. Nutation happens because of initial conditions. When you release the top, it doesn't magically know to precess it at exactly the right rate from the very first instant. There's a brief settling period. The top starts to fall a tiny bit under gravity. As the axis dips, it picks up precession speed, because the dipping converts potential energy into the kinetic energy of precession. But then the precession overshoots the steady rate. The excess precession speed has a stabilizing effect that pushes the axis back up. The axis rises past the equilibrium point, the precession slows below the steady rate, gravity starts to win again, and the axis dips back down. This oscillation repeats. It's exactly like a ball rolling in a bowl. You drop the ball in from one side. It rolls past the bottom, climbs up the other side, comes back, and oscillates back and forth around the lowest point. The top's axis does the same thing, oscillating around the steady precession angle. Friction damps the nutation within a few seconds. The bobbing dies out, and what's left is smooth, steady precession. But nutation is a real physical effect. You can measure it. Its frequency depends on the spin rate and the moment of inertia, and it contains genuine information about the physical properties of the top. I bring up nutation, not just because it's interesting in itself, but because it illustrates a general lesson. The idealized answer, the top precesses steadily, is an approximation. It's the long-term behavior after transients die out. The real behavior includes the transient oscillations. Physics is full of this pattern. We solve for the steady state because it's cleaner, but the transients are real and sometimes they matter a lot. Now I want to go deeper, much deeper. I want to ask a question that most textbooks never bother with, even though it's arguably the most important question you can ask about this entire subject. Why is angular momentum conserved? It's all very well to say torque changes angular momentum, and without torque angular momentum stays constant. But why? What is it about the universe that makes this true? The answer was given by a mathematician named Noether in 1918, and her theorem is, in my honest assessment, one of the 5 or 6 most profound results in the history of physics. Noether proved a connection between symmetry and conservation. Every continuous symmetry of the laws of physics corresponds to a conserved